Welcome to the second and final session of the BAA 2021 summer webinar. As always, we're holding the webinar on Zoom and live streaming to YouTube, and the recording will be made available to watch on our YouTube channel shortly after the presentation. You can ask questions by typing them into the Q&A and the bottom on Zoom, or in the comments on YouTube, and we'll answer them at the end of the presentation. It's my pleasure to hand over to Alan Lorraine, the President of the BAA.
Thank you very much indeed, Andy, and welcome back, everybody. So for those of you who joined us this morning, and welcome to those who are just tuning in for this afternoon. So this afternoon, we've got Dr. Amy Bonsor, who's the President of the Institute of Astronomy in Cambridge, where she is a Royal Society Hodgkin Research Fellow. And she's undertaking research into how planets form, what they're made of, and how they evolve. So she's going to be talking to us this afternoon about the intriguing title of Eating White Dwarfs. So a background previously, that sort of she did postdoctoral work at the University of Bristol and also over in France at the University of Grenoble, which is where our speaker did his degree from this morning. So she continues to study, and if you Google her on there was a huge range of work she's done, and she's a real specialist in the subject. And so we're very fortunate that she's sparing her time this Saturday afternoon to give us a talk. So without further ado, over to you, Amy. Thank you.
Thank you very much, Alan, for such a lovely introduction. Yeah, so welcome. I'm very honoured to be here to talk to you today. And I wanted to kind of talk about some of the work that we're doing in Cambridge at the moment. And I'm really interested in planets. So I put up this kind of picture of the sky behind my title slide today to kind of illustrate the fact that if we look up at the night sky, we can see lots and lots of stars. And what we're starting to learn is about the planets that orbit those stars. And what we're finding is that almost, not quite, but almost every single one of those stars seems to have a planet orbiting. And so today I'm going to really focus on the end of the lifetime of those planets. But I wanted to start out by thinking about the planetary system we know best. And that obviously is our solar system. We all live on the planet Earth, and we consider ourselves in a way to be at the center of that solar system, but we are absolutely not. Earth is teeny tiny compared to the big gas giants in our solar system like Jupiter and Saturn, and even the ice giants like Uranus and Neptune. But actually, our solar system doesn't just have planets in it. Really important to the kind of evolution and the architecture and what's going on in our planetary system are the smaller bodies, so the asteroids in the asteroid belt, the comets in the Kuiper belt, and those which are kind of scattered inwards leave the Kuiper belt and enter the inner planetary system. And also all the dust that's produced from collisions between these kind of cometary bodies. And that's the kind of dust that we know from Earth. We see it as the zodiacal cloud. There's this kind of red glow that you can see sometimes from all the diffraction of that dusty material by the sun's light. And so our star is quite typical, actually, of many other stars. There are many we're an F-type star, and there are many other solar type stars out there. But there are also stars that are a lot smaller, and these kind of going down to K dwarfs and M dwarfs, and stars that are even bigger and more massive A-type stars. And at the moment, we're kind of going through this revolution of discovery in terms of our ability to find planets around these other stars. And what we're finding is planetary systems that are nothing like our own solar system. One of the first planet, or the first planet discovery, happened by Mayer and Kellos and they found this planet that was bigger than Jupiter, orbiting on this several-day orbit around its host star, so really close in. And this is an area of our solar system where there are no planets and are totally devoid of planets. But this exoplanet discovery totally revolutionized people's thinking of what planetary systems are like, and actually whether our own solar system is really a typical or a normal planetary system. Since then, we're kind of moving more towards detecting planets that are more like our own planet Earth. We can start to detect things that are about the size of Earth and the mass of Earth, but we tend to be only able to detect them kind of close to their host stars in those inner regions of those planetary systems. But hopefully within the next kind of next decade or so, we'll move to an era where we can detect those Earth-like planets, particularly as space missions such as Plato come online. And I always kind of like to tell this story of the discovery of planets. So I already mentioned that first planet that was found in 1995. That's called 51 Peg B, and that was the discovery, the tipping point. But actually, the rate at which we found these exoplanets after that was quite slow. I remember being at school and being interested in going to university, thinking about what I could be interested in and finding out about astronomy and discovering that people had found planets around other stars and being absolutely amazed. But at the time, people would write down, and I remember seeing a slide where there were maybe 10, 12 planets written on it, and we could, that was all we knew, and those were the planets detections that we had. Then throughout my career, that number has just grown and grown, and right now we've had an explosion and we're up to almost 5,000 planets that we know around other stars. And that number is growing all the time. And I kind of like this diagram because it kind of illustrates something of the amazingness of our universe, but also kind of the ubiquitous nature of things. So what this is showing is all the host stars and all the tracks of the planets orbiting around those host stars across the night sky. And it shows that, yeah, it looks like a crazy mess really, but actually everything kind of fits together, and a lot of these, essentially this is because a lot of stars have planets. And then I said we were going to talk today about white dwarfs, these faint stellar remnants of stars like our own star, Sun. Actually, when we think about that story of when we first knew about planetary systems around other stars, well, we actually had observed the first evidence for exoplanets almost a century ago. We just didn't know that that was what we were seeing at the time. That was when we looked at this white dwarf that's known as Van Maanen's star. But it didn't look like any white dwarf that we knew. And what I'm showing here is a spectrum of that white dwarf. So it's the flux against wavelength on the bottom. So, and these kind of crazy ziggy lines are basically different spectral features. So that where the light has been absorbed by a particular, for example, calcium species in the atmosphere of that white dwarf. And so we were actually seeing this observational evidence for a planetary system already 100 years ago. So how does this work? Well, in order to kind of understand this observation, we have to think about what happens to stars. So if we start out over here with kind of our normal stars like our sun, or even more massive stars than our sun, most of the planets we know orbit these kind of low mass stars that will, when they finish burning hydrogen in their core, swell to become giant stars. When they do that, they can undergo more and more nuclear burning and get brighter and brighter until eventually they've finished up all the fuel that they have inside of them, at which point their core has collapsed downwards and it can no longer support itself. And so it falls down on itself. And the outer regions, that outer envelope of the star is unbound. It floats gently off into space. And that's what we kind of know as this planetary nebula. What it leaves behind is this faint stellar remnant known as a white dwarf. It's a very compact, dense ball of electron. So it's the electron degeneracy pressure that supports this. It's collapsed right down as far so that you've kind of got a mushy soup of electrons, essentially. And more massive stars can do other things, but we know less about the planets around them, and these would be much more dramatic events in evolution. So down here on the bottom channel, you can see how a more massive star becomes, again, a giant star. Well, it keeps burning all the fuel in the center, and then instead of just collapsing and floating off, it actually explodes in this humongous supernova, leaving either behind a neutron star or a black hole. So if we think about this kind of path up here, and we can think about what happens to the planets while they kind of sit around this path. And actually, most of that planetary system is relatively unaffected by this evolution. Maybe planets like Earth will be quite affected by this giant star swelling up and getting very, very hot. But if you're sat out on Jupiter or in the Kuiper belt, then you're not really so bothered by this massive giant star that's going in the middle. And when the planetary nebula floats off, it floats off actually quite gently, at very low density, that there's actually very little interaction with the planetary system there, leaving you with a planetary system orbiting your white dwarf. So I said white dwarfs are the kind of faint, compact remnants that were left at the end of the lifetime of a star like our sun. And these are really incredible objects. I find them absolutely fascinating. And one of the most fascinating features about them is that you've essentially taken the mass of something that's almost the mass of the sun, maybe it's lost a bit, maybe it's half the mass of the sun, and you've squished it down into something the size of Earth. So there's really, really strong gravity there. And that makes for exciting effects when you study that kind of matter. It's the kind of matter that we never find on Earth. But it also makes for an interesting effect when we observe those white dwarfs. But firstly, I'm going to go back to that story of what happens to our solar system when the star evolves to become a white dwarf. So if we think of our solar system today with these terrestrial planets in the inner region, asteroid belt, gas giants such as Jupiter and Saturn, and then these ice giants, Uranus and Neptune, and then the Kuiper belt in the outer regions. So when that star swells to become a giant star, that additional heating is going to really infect these inner planets. And in fact, the star is going to get so massive that it can engulf Mercury, Venus, and maybe even Earth. Like, it depends on exactly how you understand the tidal evolution of these stars, which are poorly understood as to whether Earth gets enveloped or not. But for these outer planets, they may get heated a little bit more, but they were quite cold before, so they're not too bothered by that. And the main effect is that when this star loses mass and everything floats off in this planetary nebula, the gravitational pull of that inner star is less, and that means that the outer planets, their orbits widen. So now Jupiter is further from the star, so are the asteroids. And so you end up with this very strange planetary system where the star is now tiny as the size of Earth, and the orbits of the planets have got even bigger, and there's this great big hole in the middle. But then what's interesting about this system is that it's going to be less stable dynamically than the system in our solar system. So over many, many hundreds of millions of years of evolution, the planets in our solar system did this kind of jiggly dance whereby they wriggle together and kind of knock each other a little bit out of place until they find the perfect combination where, so Neptune's sculpting the edge of the Kuiper belt, for example, and chucking comets out the planetary system, Jupiter's removing things from the asteroid belt. And every now and again, we get some of these cometary bodies, for example, or things that get scattered right into that inner solar system. And we see those are the comets that we can observe, are the ones that come past Earth. And we even have a population of comets that are sun-grazing comets. And so those are things that go really close to the sun, where the sun heats them up and they expel gas and dust. And that's very easy for us to observe. Well, that system then was nice and stable and stopped doing quite so much scattering by the time it got to the white dwarf phase. You've lost some mass. And so the planets are saying, hey, I'm bigger now. I've got more mass than compared to that sun, so I can do some scattering again, and I can jiggle those asteroids and I can jiggle those comets. And most of that kind of interaction leads to comets and asteroids being ejected, flung out of that planetary system. But every now and again, sometimes things are flung inwards towards that white dwarf. And what's interesting is they don't have to do a bullseye and hit the target of that white dwarf. Because the gravity is so strong, they can actually hit an area that's about the size of the sun around that white dwarf. And from there, they will then be torn to pieces by that strong gravity and can end up going into that white dwarf. And so this is an artist's impression of what an asteroid that's kind of flung inwards towards this white dwarf and then torn apart by the strong gravity might look like. Where you've got the white dwarf in the middle here, and this asteroid has been broken up into rocky fragments, which then collisionally grind down. And what happens is they actually end up entering the white dwarf through this kind of dusty gas disk. They end up going into the surface of the white dwarf, and that's hence the title of my talk, that essentially these white dwarfs are planet-eating white dwarfs. So how do we know about this? Well, we know about this because we can observe white dwarfs and we can see features in their spectrum that we didn't expect to be there, just like we did for Van Maanen's star, and now we do for almost 1,000 other white dwarfs. And those features are from that planetary material, that asteroid or that rock that was flung inwards and ended up entering the white dwarf atmosphere. So this is again a spectrum, which is brightness as a function of wavelength, and you can see the spectral signatures for different elements. So they're all color-coded here by the different lines: iron, magnesium, calcium, and so you can see the different species that we're observing in the atmosphere of this white dwarf. So if any of you know anything about stellar spectroscopy, you'll say, well, actually, this is a really boring spectrum compared. If you looked at the spectrum of the sun, you would see a vast plethora of different lines, and there would be all kinds of things going on, and that's absolutely true. But that all comes down to this special feature of white dwarfs. So I said that white dwarfs are kind of these compact remnants of stars like our sun, and the gravity is really, really strong. And that strong gravity means that things sink downwards, and we can calculate the timescale on which they should sink downwards. And so everything's sinking in. It's rather like throwing a rock into a pond. The rock doesn't hit the bottom immediately, but you can watch it kind of sink down, and then you wouldn't see it anymore. So if you were taking a photo inside of the pond, most of the time you would look at the pond and you would just see water. But every now and again, if there were rocks being flung in constantly, you would capture a rock in the process of being flung in. And that's exactly what's going on with the white dwarfs. So if you imagine the white dwarf being this kind of mass of material in the center, that's kind of this electron degeneracy soup that's supported here, and then this very thin atmosphere on those outer layers. And that atmosphere is the only bit we can see. We're looking in, when we look at those spectrum, we're just seeing within the atmosphere. And normally for a white dwarf, that atmosphere would only have hydrogen and helium in it, because all those heavier metals, just like the stone in the pond, they would all have sunk out of sight and we wouldn't see them. But if we've got this asteroid that was flung in and is constantly throwing essentially stones into the atmosphere, well, sometimes we can catch them and we can observe them in the spectrum of that white dwarf. And what's really neat about this is that we can use these to really see what's inside of a planetary body. It's almost like taking that planet to pieces and looking at everything that was there. We can say, well, what was the calcium to iron ratio inside of that planetary body? What was the chromium to iron ratio? What was the carbon to oxygen ratio in a cometary body? And these are even things that are hard to observe for comets in our solar system, where we can only really, from spectroscopy, look at the surface. We can't see what's going on in the deep interior. And so these rocks, these metals in the atmospheres of white dwarfs, have this really unique role to play in our understanding of what planetary bodies are made from. So this is just a kind of very simple diagram to illustrate something of what we're learning about what planets are made from these white dwarfs. So on the right here, we've got two pie charts that are showing us, firstly, the kind of bulk composition of our own planet, Earth. And what's I find absolutely amazing is that actually, although like we know that we can look at rocks in mountainous regions and we can see this wide variety of different kind of rock formations, different geologies going on, actually, the vast majority of things on Earth are really built out of 4 elements. Those are the 4 elements that dominate our mass budget: iron, silicon, magnesium, and oxygen. Everything else kind of fits into this small wedge here that's been left over, but it can be very, very important and significant things. If we were a comet instead, so we had lots of ice as well as these rocks, then exactly the same, we'd still be dominated by those 4 species: iron, silicon, magnesium, and oxygen. But we would also have water, so there'd be a lot more oxygen from the water, and lots of carbon ices, things like CO2 and CO. And so the carbon, the oxygen, those volatiles really dominate the abundances iron comets. And so one of the things we can see from looking at different white dwarfs where we see planetary material in the atmosphere and we can work out the compositions, we can say, oh, are they comets or are they things like Earth? And so over here, I've got 5 examples. We now have many, many more than this, but I thought this diagram really kind of nicely illustrates so that you can see the different compositions from these five white dwarfs. And the first thing you'll notice is that just like our own planet Earth, we're really, really dominated by the same species, iron, oxygen, silicon, and magnesium. But you can see that the budgets are very, very different. So for some of these white dwarfs, there's much more oxygen, maybe hinting that we had water ices there. For some of them, there's lots and lots of iron, which tells us about different kind of mineralogy. The magnesium to silicon ratio changes between these, which is very important because it tells us exactly about some of the chemistry of the rocks, for example, olivine rocks versus phosphorite rocks. And so we can learn from these white dwarfs lots and lots about what's going on in terms of the composition of planetary bodies. And so now I'm just going to talk for the last 5 minutes in detail about one specific thing that we've learned from looking at these bodies in the atmospheres of white dwarfs. And in order to think about that, I kind of always like to start by thinking back about our own planet Earth. And so this is a lovely picture taken from space of our planet. We live on the surface of our planet, and yet it's only in the last 100 years of our existence that we've really started to understand anything about the deep interior of Earth. So whilst we can measure the rocks on the surface, we can understand what's going on. Understanding the interior, Earth's interior, is very important for understanding what's going on the surface and, in fact, our own existence and how that came to be. So we see clearly from this image that there are continents as well as oceans. And we know that the existence of these continents kind of points towards that idea of plate tectonics, and the idea that we have a crust and we have material that can kind of disappear into our molten mantle underneath. But actually, deep in Earth's center, we have this liquid iron core. And the existence of this core within our own planet, we think is something that's fairly typical of other planets within our solar system, at least, and including many of the asteroids in the asteroid belt. But it points to this phase early during the evolution of all of these bodies where everything was largely molten. And so for Earth, we call this kind of the magma ocean phase that happened in the late stages during the formation of our own planet. And you can kind of imagine that this molten planet then, the iron was able to form droplets which kind of rained down to the center because they were heavier than everything else, leaving behind this silicon mantle. And this is a key importance even to the existence of people and life on Earth. And the question is, does that happen in planetary systems outside of our own solar system? Would we expect other rocky planets that we see, would we expect them to have gone through a similar phase where they were molten and the iron sunk to the core to form this kind of what we call a core mantle differentiated planetary body? And so core material is very, very rich in iron. And when we look at planetary bodies that we can see in the atmospheres of these white dwarfs, well, we can see how much iron is in them. So we can ask the question, well, did they form a core? And most of them haven't done. But this is one example where there is lots and lots of iron in this planetary body. And what we think we're seeing is that actually the white dwarf has accreted something that was basically a chunk of core material, or it was a kind of mainly the core with a little bit of mantle added on. And so this plot is just showing the abundances of 4 key elements: calcium, iron, silicon, and an upper limit for oxygen. So these are what we see in the atmosphere of the white dwarf, relative to magnesium and relative to the solar abundances. That's just a way astronomers like to plot things. And this kind of grey region here is what we think the abundances would be in a normal. If nothing was going on, they would all sit within this grey region. And actually what this is it's the abundances that we see in other stars in our universe. So where nothing really has changed. And what we see for this object is that we've got lots more iron. This is a huge amount more iron than we would expect. And that we think the explanation for this is that it's accreted something that's core rich. Yeah, so we also see, just to kind of before I go on, we also see bodies that look mantle rich, that are really depleted in iron. And we've even got a few objects that look more like they're kind of crustal and have this kind of element abundance of something that's crust rich. Cool, so just to finish off, I wanted to kind of show one more thing, which is about how we can observe this process of asteroids arriving into our planet-eating white dwarfs. And so just to remind us, these asteroids get flung inwards and they get close to that white dwarf within a solar radius, so actually it's a huge area around that white dwarf. They get torn apart and into lots of kind of chunks of dust and rocks, which then circulate in this disk whilst they're moving onto the white dwarf surface in this accretion phase. And very excitingly already, now in 2014, we discovered a white dwarf where we can see evidence of these asteroids near to that white dwarf. So these are asteroids that are on a 4-hour orbit around this white dwarf. And during that orbit, there's like kind of asteroids and dust, and it blocks the light from the white dwarf to us. And we can see that, just like detecting a planet, the planet would block the light coming from the star towards us, and we would see a dip in the stellar luminosity. And we see this for this white dwarf. So this is showing the brightness or the flux from that white dwarf as a function, as part of the orbital periods. This is actually phase routes, but essentially it's just as a function of time. And what you're seeing is that every now and again during this orbital period, there's lots of dusty material that we think comes from these asteroids orbiting this white dwarf that's being kind of flung off and is blocking the light that we're getting from this white dwarf. And this continues on a 4-hour period, on and on and on. And the star seems to go through periods when it's very, very dusty and there's lots of material blocking it, and periods when it's a lot quieter and maybe there's less dust, less asteroids that are being flung in. And we're really, really excited about this, as finding out and understanding exactly how these planetary bodies arrived into the atmospheres of this particular white dwarf. Yeah, so I'd just like to finish there and say I hope I persuaded you that we can learn something about what planets are made from looking at those faint stellar remnants of stars like Sun that are known as white dwarfs. And I'm really excited about the next kind of 10 years of discovery in this field, because we really are moving from looking at individual white dwarfs to study the composition to an area where we can study the population. And hopefully I persuaded you that white dwarfs are not at all boring, and actually we can learn a lot from these very faint remnants of stars like our Sun. So thank you very much for your attention.
Thank you, Amy. That was a fascinating talk on a very innovative field of study. I see we've already started getting a few questions in, but just to remind anyone who joined late, you can ask questions by typing in the Q&A on Zoom or the chat on YouTube. And we have about 40 people with us this afternoon, in spite of, I think, someone mentioned that there's the Lions match and also Wimbledon, which we're competing against. First question's from Dal Dobbs, and he's asking, have you found any exoplanets within the Roche limit of the white dwarf, and does this imply it's being torn apart?
So that star that I showed at the end was WD1145. We're seeing essentially what we think kind of asteroids rather than a planet, but in the process of being torn apart, and we're seeing that body block light from the star. And there are now, I think there are 2 or 3 more objects where they're doing the same thing. We just haven't studied them quite as well. That's a very good question.
Thank you. And then we have Bruce Fairbanks, who asks, are most white dwarfs about the same size, or are they quite variable in size?
Now, that's a very good question. So astronomers like to think in orders of magnitude, and in terms of orders of magnitude, white dwarfs are all exactly the same size, which is something relative to our Earth. But actually, we do see quite a variation in mass of white dwarfs. And we can measure that very easily. So we can see the width of the lines. And so we can tell you that there is definitely a variation in the mass of the white dwarfs. But we're not able to resolve exactly the radii. And so that always comes from modeling, but it would correlate approximately, I think, with the mass.
Thank you. And so along similar lines, but well, kind of, is there a max? This is from Pete Sherman about the mass, and is there a maximum minimum mass of a star? Sorry, of a parent star that will end up as a white dwarf?
Yeah, that absolutely is. So stars like our sun will definitely end up as white dwarfs, and stars that are significantly more massive. I'm not going to give the exact limit, but it's somewhere between 5 to 10 solar masses. Then you move on to that other track where you're then so massive that you do multiple phases of stellar burning and instead explode as a supernova. And in terms of minimum mass star, well, we have to think of kind of brown dwarfs as being those faint stars where nuclear burning in the center of them hasn't necessarily ignited, and so therefore they won't necessarily lose the outer regions and move to the white dwarf phase.
I think, or I guess as well, with the very lowest mass stars, actually there hasn't been enough time since the universe began for them to actually evolve and become sort of anything other than a main sequence star.
Yeah, absolutely. And actually that means that we're dominated. So our white dwarf population is dominated by stars that are slightly more massive than the sun for that reason, because those are the stars that evolve fastest and therefore end up dominating the white dwarf population.
Thank you. Then we have William Scutcher, who asks, what techniques and equipment are used to make the observations? Yeah,
that's a very, very good question. There's a lot of different things. So I think I've shown two things. One was spectroscopy, so these spectra, and for that we use instruments that are very good at spectroscopy. So for example, on the VLT, the Very Large Telescope, there's an instrument called X-Shooter that was where those observations that I showed came from. And we also use the Hubble's telescope, Space Telescope, which is really good for finding things like carbon and oxygen. In terms of the transit observations that I've shown, you can do those with any telescope that can do good photometry. And actually the star is okay at 17th magnitude, so it's not super bright, but it's actually accessible to a lot of really small telescopes. And what's kind of been nice about this object has been followed up over the last 5 years by a whole range of kind of 1 to 2 meter telescopes around the world.
That's very interesting because, yeah, there's some large amateur telescopes which tend not to be that size, but they're kind of knocking on the doors of being able to do about sort of 17th, 18th magnitude photometry.
Yeah, absolutely. So amateur astronomy has been really important for this object. So if anyone's interested, you might be able to do some good science. Thank
you. And although we have amateurs doing spectroscopy, it tends to be on the brighter objects because it's just yeah, the white dwarfs are just too faint to reach unless you've got something like the VLT. Yeah, absolutely. I was going to say it's even with spectroscopic surveys, these things we can do it and we can do spectroscopy on white dwarfs, but they are very much on the faint end of what people are used to. Yeah. A slightly off-topic or different question comes from David Swan, and he was just at the start. He was saying it's a lovely pic, and he was wondering if it was the comet C2020 D1 Swan in the vicinity of the Triangulum galaxy. Was that one of the images I was showing? I think it might have been right at the very start. I'm not sure. And we have some very keen observers in the BAA, yeah, so they may well have spotted the probable source of the knowing some of the bright comets which have gone nearby. Interesting. Yeah, I'm honestly not sure which. Yeah, that would be it. So I think your second slide, was it second or third? Oh, so this is an artist's impression. Yeah, and I think the next one, is it? Or previous one to it? It was, yes, that one. I think is what David thought. So this is I think was supposed to be Sirius B and the night sky. Okay.
Yeah.
We have.
I will defer to more expert people than me, however.
Then we actually had a couple more questions coming in the meantime, which is
Cool.
Hazel Collett. And hello, Hazel. And we should say a thank you to Hazel for organising these webinars. Hazel organises in normal times our meetings, but she's been hard at work behind the scenes organising speakers for the webinars, as well as getting ready for when we're able to have face-to-face meetings once again. And Hazel asks, is there a point when the white dwarf cannot eat any more planets, even if there are still planets around it?
It's a very good question, Hazel. Thank you. And I wish I knew the answer. I think we don't really know, actually, because we can't see the planetary systems that are around these white dwarfs. So we only see evidence that they're eating them, right? We don't know what's there. And we see that about between kind of 20 and 50%, some people reckon, of white dwarfs are doing this, so have these metal lines in their atmospheres. And so my suspicion is that mostly we're doing this at a very low level, and it's a tiny amount of material that's going into the atmospheres of those white dwarfs. Maybe sometimes we can see things that's equivalent to kind of a 50-kilometer sized asteroid in the white dwarf right now, and it will sink out before more material comes in. So I think we're never kind of at the rate where we would saturate, so to speak.
Thank you. And then we do have another question in from Darryl Dobbs, which is it just visible light you can make observations with, or do you also use radio, sort of microwave, and other parts of the spectrum?
So we don't tend to use radio and microwave, but we do use UV, and UV spectroscopy has been very, very important for these observations, because there are particular lines of particular elements like carbon and oxygen in the UV that you can't see anywhere else. And so they've been really important about telling us about the volatile composition of these planetary bodies. Great,
and thank you very much. I think looks like it's it for the questions. I can't see anything coming in on YouTube. We do have some comments coming in, which is super talk, thanks, and from John Evans, and very interesting from Peter Sherman. And also just to remind everyone that the recording from this morning's talk will be available on our YouTube channel, as will this one, once YouTube's done its processing. And then in mid-July, on Wednesday the 14th of July at 7 p.m, we have the director of the BAA Jupiter section, Dr. John Rogers, giving us a talk on Jupiter rising. So if there's no more questions coming in, I'd like to thank Dr. Amy Bonsor once again for coming and giving us this fascinating talk on a Saturday afternoon. It's at least sunny here in the southwest.
Yeah, it's sunny here in Cambridge too. So thank you very much for all the interesting questions. It's been a pleasure.
Thank you. And we hope to see all the attendees at another webinar soon, and who knows, maybe in person to person before too long. Thanks all.
Bye.
Hi, Amy.
Bye.
Just to say very quick thank you for me as well. This was an excellent talk, and thanks, as I said, for giving up your time. So,
yeah, no, thank you very much for inviting me. Yeah.
okay.
And thanks also to Hazel for the organising.
Goodbye, everybody. Bye.